Hello friends, welcome back. In this video, we have to study the electroneutrality principle. Here, this principle is explained by taking an example of FeH2O6 3+. So let's start with this electroneutrality principle. Now here we can see that one of the limitation of valence bond theory was that there would be an accumulation of negative charge on the central metal atom or the ion during the formation of complex. What is the meaning of this? We know that in a complex at the center we are having the metal. It is surrounded by the number of ligands, and while forming a complex we know that the ligand must have at least one lone pair of electrons. So to form the coordinate or the dative bond, the electrons they are donated from ligands to metal. So as there are more number of ligands and a single metal, there would be the accumulation of negative charge on the central metal atom or the ion, right? Then we can say that the charge developed on the metal and the ligand due to shift of electron pair is called as the formal charge. And the formal charge is obtained by subtracting the original charge on the metal from the total number of electron pairs shared between the metal and the ligand. So let's take an example for this. We are having the first example, FeH2O6 2+. So we have to find out the formal charge. The original charge on the Fe is +2. How it is +2? This water is the neutral ligand, and the complex we are having the +2 charge. So this Fe is also having the +2 charge. Then total number of electron pairs. Now as there are 6 ligands, so there should be the 6 electron pairs, which is -6. Then the formal charge becomes the -6 + 2, and which is equals to -4. So the formal charge here is the -4. The second example FeH2O6 3+. Again the original charge on the Fe is equals to +3. Then total number of electron pairs, which is again the same, that is the -6. Thus the formal charge is equals to -6 + 3, and which is equals to -3. One more example, that is FeCN6 4-. So first of all, the original charge on the Fe is equals to +2. How it is +2? Now cyanide is the negative ligand, and one cyanide is having the -1 charge, so it is total having the -6 charge. So it becomes +6 - 4, which is equals to +2. So the original charge on the Fe is equals to +2. Then the total number of electron pairs, as there are 6 ligands, there are 6 electron pairs, so which is equals to -6. And hence the formal charge is equals to -6 + 2, which is equals to -4. So in this way we can find out the formal charge. Then the Pauling suggested that such a situation would not arise due to two reasons. Which type of situation? That means the imbalancing of the electrons on the metal as well as the ligand. The first reason is that generally ligands are fairly electronegative, and hence the electrons would not be shared equally between the metal and the ligands, thus inducing positive charge on the metal to balance the unfavorable formal charge, right? And the second reason is the complex would be most stable when the electronegativity of the metal was such that the metal would achieve a neutral condition. So these are the two reasons which are given by the scientist Pauling. And this is known as the electroneutrality principle. So this rule is known as the electroneutrality principle. Means in short we can say that the electrons, they are neutralized, and hence it is electroneutrality. So the Pauling's electroneutrality principle states that electrons are distributed in a molecule in such a way as to make the residual charge on each atom 0. So each atom should become the 0, except that hydrogen and the most electropositive metals can acquire the partial positive charge, and the most electronegative atoms can acquire the partial negative charge. This is called as the electroneutrality principle. The charges on the atoms can be decreased by a change in the polarity, or the second one, a change in the amount of ionic character of a bond, or a third one, a change in the amount of a multiple bond character of a bond. This principle is applicable to complexes which are unstable due to accumulation of excessive negative charge on the metal. So that was a limitation of VBT. In such complexes, we can say that the bonds are partially ionic and partially covalent. So let's explain this by taking an example of FeH2O6 3+. The structure that we have seen in the first slide only, FeH2O6 3+. Now if all the FeO bonds are 100% ionic, you have seen in the structure the Fe is attached to the oxygen, and if all the FeO bonds are 100% ionic, then what we can say, then the entire charge, the entire +3 charge would be located on the Fe atom only. That is, electrons are not shared and the electrons of the ligand remains with the oxygen atom only. The structure would be like this. We are having the Fe, it is surrounded by the 6 water molecules in which oxygen is attached to Fe, and here the bond between FeO is the 100% ionic. So this +3 charge would be located on the Fe atom in the 100% ionic bonding. Then this is called as a 100% ionic bonding. Further, if all the FeO bonds are 100% covalent, 100% covalent means there is an equal sharing of electrons between Fe atom and the oxygen atom of ligands. So thus in the 100% covalent bonding, each oxygen atom gets +1 formal charge. That means Fe atom would be left with -6 + 3, which is equals to -3 formal charge, right? So this is the structure. In this structure, the Fe atom would get the -3 formal charge and each oxygen atom would get the +1 formal charge. So this is for the 100% covalent bonding, means there is an equal sharing of electrons between the metal and the ligand. Then the third type, if all the FeO bonds are 50% ionic and 50% covalent, that means each oxygen atom would get +½ formal charge. So Fe atom would get -½ formal charge per shared pair of electrons. Since Fe shares 6 electron pairs, that is 6 into -½ which is equals to -3 charge. So the charge on the Fe becomes -3 and the charge on the complex becomes +3. So there will be the cancelling. So it is neutralized, which would be cancelled by the original +3 charge, right? Thus the residual charge on the Fe would be 0. So in this way we can apply the electroneutrality principle. That means the electrons are neutralized, or we can say that the residual charge on the Fe would be 0. But here we can say that the oxygen atom would be reluctant to bear the positive charge. That is right, because it is an electronegative atom. So the electrons from the adjacent, which are the adjacent? Adjacent are the hydrogen atoms, would be displaced towards the oxygen atom. That means oxygen atom is attracting electrons from the adjacent hydrogen. So the net effect would be that each hydrogen atom would get +1/4 formal charge. Thus oxygen atom becomes again the neutral, right? So oxygen taking the electrons from the adjacent hydrogen and each hydrogen get the +1/4 formal charge. The +3 charge which was distributed on 6 oxygen atom would be now shared by the 12 hydrogen atom when the bonds are 50% ionic. Thus the shift of electron pairs and the charge distribution takes place in such a way that the formal charge, that is a -3 on the Fe atom, is neutralized, and this gives stability to the complex, which can be shown as, so we are having this complex atom in which we are having the Fe at the center, which is surrounded by the 6 water molecules in which Fe is attached to oxygen, and each oxygen is having the +½ formal charge, right? Then we are having the second structure in which there are 12 hydrogen atoms, and each hydrogen atom will get the plus 1 by 4 formal charge to make the adjacent oxygen atoms neutral. So in this way, the residual charge on each Fe will be neutralized, which is called as the electroneutrality principle. So here it is the 50% ionic bonding and 50% covalent bonding, due to which the residual charge becomes zero, or the residual charge is neutralized, and this is called as the electroneutrality principle. Thank you. In the next video, we have to study the multiple bonding, that is d pi p pi and the d pi bonding. Thank you very much.